In this video, I want to go through a couple of old exam problems that I've given in statistics courses. One problem, an F-test to compare variances, and another problem, a T-test to compare means. We'll use technology and we'll also look at tables. So the first problem is about comparing variances. In a series of experiments to determine the absorption rate of certain pesticides into skin, measured amounts of two pesticides were applied to several skin specimens. After a time, the amounts absorbed in micrograms were measured. For pesticide A, so we're comparing two things here, the variance of the amount absorbed in 6 specimens, so it's a sample of size 6, was 2.3. That would also mean the standard deviation would be the square root of 2.3. While for pesticide B, the variance absorbed in 10 specimens, so this is a different sample size, 10, was 0.6. That would also mean the standard deviation would be the square root of 0.6. Assume that for each pesticide we are collecting independent random samples from normal populations in each case. Do we have enough evidence to conclude that the variance of the amount absorbed is greater for pesticide A than for pesticide B at the alpha equals 0.05 or 5% level of significance? It certainly does look like with the samples, certainly 2.3 is bigger than 0.6, but is it a significant difference? Is it statistically significant? Is the p-value we compute going to be less than 5% or not? We actually have to do the calculation. All right, so the relevant statistic to use is called the F statistic. It is the ratio. If you're setting up the test, we should set up the test first, excuse me here. The null hypothesis would be that these variances are equal, the population variances. For pesticide A, we could call the population variance sigma sub A squared. And for pesticide B, we could call the population variance sigma sub B squared. And we are wondering, is pesticide A absorbed more than pesticide B, or is the variance bigger? So we're wondering, is sigma sub A squared bigger than sigma sub B squared? That would be our alternative hypothesis, which sometimes I call H1 and sometimes we call HA. Is sigma sub A squared greater than sigma sub B squared? That's the question. So yes, the F statistic is what you want to use. The formula for the F statistic uses the sample variances S sub A squared divided by S sub B squared. And the way you want to do the test, if it's a right-tailed test like this, is you do want to have it set up so that the bigger one is on top of the smaller one. You want to typically think of this in terms of something that's going to be bigger than 1, significantly bigger than 1, giving you significant evidence against the null hypothesis that they are equal. Okay, so what does that equal here? Based on these given numbers, which I'm just giving you the summary statistics rather than the data, the sample variance, this is assumed to be a sample variance because it's coming from a sample, for A is 2.3, and the sample variance for B is the 0.6. And again, these are variances. If you were given standard deviations instead, you would have to square them before you compute this ratio. And so what do we get here? 2.3 divided by 0.6 gives 3.83 with a 3 repeating, approximately 3.83. Okay, so how do we now do this test? With technology, we can do an F test. We do need to know the degrees of freedom that are associated with this F statistic. There's certain degrees of freedom for the numerator and the certain degrees of freedom for the denominator. I could write df num for numerator. That's n sub A minus 1, the sample size for pesticide A minus 1, and the degrees of freedom for the denominator, n sub B minus 1. The sample size for pesticide A was 6, so 6 minus 1 is 5, and the sample size for pesticide B was 10, so this is 10 minus 1 is 9. So if we use the technology, if we use the F test in a TI graphing calculator, by going to the stat menu and going over to tests and going down to, there it is, 2 sample F test. We can either use data or stats. I don't have data here, I only have stats. So go ahead and, oh, careful here, you got to plug in standard deviations, not variances. So This is not going to be 2.3, but the square root of 2.3, raise it to the 0.5 power. That's the standard deviation for A. Sample size here for A is 6. For pesticide B, the standard deviation is not 0.6, but 0.6 squared. Or excuse me, to the square root, 0.6 square root. And the sample size was 10. We are doing a right-tailed test. This is going to calculate a p-value. I could have also had it draw it. The p-value would be an area to the right. Yes, we confirm the F statistic value is 3.83 repeating, and the p-value is about 0.0387. The p-value is about 0.0387. That is less than 0.05, which is our given alpha. So we would say we do have statistically significant evidence against the null hypothesis at the 5% level, at the alpha equals 0.05 level. So we would reject the null. And so our final conclusion, as far as the question goes, do we have enough evidence to conclude that the variance is greater, again at this level? We would say yes. When the p-value is smaller than the given alpha, that's when you say you have statistically significant evidence against the null hypothesis at that level of alpha, so you reject it. Now, technically speaking, for honesty's sake, when you set up such an experiment, you should decide on what alpha should be ahead of time. Alpha is also the same as the probability of a type 1 error, so you are thinking about what are the consequences of a type 1 error, and if they were really bad, then you'd want to set alpha even lower. Variances, whether variances are equal just sort of determines what you would do to compare means ultimately. We're going to see that in the next problem. So it's maybe not necessarily a bad thing if you make a type 1 error, maybe not necessarily a big deal, but that's what you want to think about. This is not less than 0.01. So if alpha were 1%, we would not reject the null. It would not be statistically significant at that level. Again, alpha is the probability of a type 1 error. Okay, so that's the first problem. That's comparing variances. Now let's do the second problem, comparing means. Environmental testing is an attempt to test a component under conditions that closely simulate an environment in which the component will be used. So some sort of electrical component here. I guess we're testing in the environment. 2 different locations in Alaska. Before the testing can be conducted, it is necessary to determine soil composition in these localities. These data are obtained, so we're not looking at the raw data again. I could have done that. You could deal with raw data, but we're dealing with summary statistics. In the city of Anchorage, we got a sample of size 10, and the mean percentage of, I don't even know what that molecule is, silicon oxide or something perhaps, by weight in the soil. The mean is 59.94. I guess that would be a percent of something. And the variance is 9. And in the town of Kodiak, the sample is size 16. The mean's a bit less, and the variance is also a little bit less. Part A says find the p-value of the test of the null hypothesis that the means are equal versus the alternative that the first mean is greater than the second mean. And again, for honesty's sake, you'd want to set up the hypotheses ahead of time. I'm not saying what alpha is in this problem. We're just making a decision ultimately based on the p-value and if it just seems small. Under the assumption here in part A that pooling of variances is appropriate. Okay? Show your work and explain. To decide if pooling is appropriate, we'd have to do the F-test to compare variances, but I'm not doing that in this problem. Population variances with the sample variances. And part B is find the p-value of the test under the assumption that pooling is not appropriate. And there we're going to use technology, use the calculator. We'll use the calculator in both cases, actually. Though in the second case, the calculator is definitely necessary for figuring out the degrees of freedom because it's different when you do not pool. All right, start with part A. So we're assuming pooling is appropriate. We do need to compute a t-statistic. The formula for the t-statistic in this case is x1 bar minus x2 bar divided by, when pooling is appropriate, the square root of the square of the pooled proportion, which could also be factored out of the square root and written as a standard deviation of a pooled standard deviation, times 1 over the first sample size plus 1 over the second sample size. And the degrees of freedom to use here, sometimes called df, sometimes called gamma, by the way, in this context, is n1 plus n2 minus 2 when pooling is appropriate. This is the df that we use. Notice this is the same as n1 minus 1 plus n2 minus 1. That is the degrees of freedom to use in this context. That's going to give us 10 plus 16 is 26, minus 2 is 24. That's the degrees of freedom to use here when pooling is appropriate. So now we actually have to compute this. x1 bar minus x2 bar is 59.94 minus 57.06. What is the pooled proportion? I haven't told you the formula for that yet. It's a special kind of weighted average. The pooled variance, excuse me. The pooled variance is a special kind of weighted average of the other variances. Did I say pooled proportions more than once? I might have. I don't remember. So the weighted average is this. It's n1 minus 1 times the first variance plus n2 minus 1 times the second variance, all divided by n1 plus n2 minus 2, that degrees of freedom. So in this case, n1 again is 10, so we get 9 times the first variance. The first variance is 9. And then n2 minus 1 is 15 times the second variance, which is 7.29, all divided by 24. So that's going to be 9 times 9 is 81, plus 15 times 7.29 is 190.35 divided by 24. It's about 7.93125, I guess exactly. And that's what's got to go in this formula. Notice this is between these two numbers. Right there and there. A little closer to the second one because it's got a little more weight because the sample size for Kodiak is a bit bigger. So we have 7.93125 times 1 over 10 plus 1 over 16. All right, so let's do that now. Times 1 over 10 plus 1 over 16. And then we take the square root of that. Okay, so this entire thing is this 1.135265663. Do 59.94 minus 57.06, which is 2.88, and divide by that previous answer. The observed value of the t statistic, which is often called little t, by the way, is approximately 2.537. Okay. Guess I'm doing this two ways here. It's worth calculating this, but I could have also just done a t-test right away. So let's get the p-value in two ways here. I could do it with the stat menu and the t-test. I could also do it with the distribution menu above the variables button. Distribution menu, go down to TCDF. Effectively, the lower is minus infinity, and the upper is 2.537. There's 24 degrees of freedom. This is going to give us the area to the left of 2.537. The p-value for a right-tailed test is going to be the area to the right of it. So I need to do 1 minus this number. The p-value is about 0.009. Let's confirm that with the t-test as well, which I could have done right from the start, but I think it's worth emphasizing the formulas here. Stats, test, 2 sample t-test is what we're doing here. We are doing statistics, not data. x1 bar, again, is 59.94. This is going to be the square root of 9, which is 3. Sample size is 10. x2 bar is the 57.06. 7.29 to the 0.5 power is the standard deviation of the second for Kodiak, and n2 is 16. And we are doing a right-tailed test. And we are, yes, pooling for this part. calculate. It's going to be an area to the right. And yes, we confirmed the t-stat about 2.537 and the p-value is about 0.00009. Less than 1%. There's no alpha that's given. This is small enough to reject the null, right? Though we would typically reject the null in this kind of situation. So my decision would be to reject the null. It doesn't ask for a decision, but just a p-value. If it did ask for a decision, I would say reject the null. It seems like we've got strong evidence that the mean silicon oxide, or whatever that's called, in Anchorage is greater than that in Kodiak. That is the p-value there. Notice the degrees of freedom is confirmed to be 24. Notice also there's the pooled standard deviation. If I square this number, I should get the 7.93125. Let's confirm that. 2.8162 squared. Yes, is very close to this up to rounding error. Okay? All right. What about part B? We'll do that quicker. And I'll write a formula for the t-statistic, and I'll say the degrees of freedom, though the degrees of freedom will be based on technology, but then I'll just use the technology for part B when pooling is not appropriate. In part B, the t-statistic in this case, you're not pooling the variances to get a better approximation for the common population variance. Instead, you are thinking about each variance separately. The formula ends up being, take this and divide by the square root of S1 squared over N1 plus S2 squared over N2. And notice, by the way, if you replace both S1 squared and S2 squared with SP squared, you would get this formula back up here. But what is the degrees of freedom? Degrees of freedom is a big question mark. The old way of doing things was to use something called the Smith-Satterthwaite formula. But now we're just going to use technology for the degrees of freedom, and we'll also use the technology to do the t-statistic calculation. It will give you a slightly different t-statistic than we got before. We'll get something slightly different than 2.537 because we're dividing by something different. It'll be just a slight difference. The p-value will be slightly different, partially because of that, and partially because the degrees of freedom will be different. I think the degrees of freedom will probably end up being smaller. That's what typically happens. So go back to the stat menu, go over to tests. We're doing, again, a 2-sample t-test, and it's the same numbers as before, except now we are not pooling. And it actually even gives you a DF that's a decimal. It's not even a whole number, 17.69767 for the DF it gives you. That's technology. Let's just round to 17.7. The t-statistic value, which we should report here, is 2.474. Yes, that is a little different than 2.537, again, because we're dividing by something different. You could double check by computing this that we get that. I won't take the time to do that. And the p-value is a bit bigger, 0.012 if we round to the same number of decimal places up there. That's what's typically going to happen when you do not pool. So you get a lower DF and a higher p-value. And that is playing it a bit more conservative, you might say. It makes it harder to reject the null. I mean, this is still small, so we're still going to reject the null, most likely. But it does make it a little harder, and that some people feel is always a good thing. And so some people always pool. Another thing you can do is you can even round this down to 17, or you can even play it extra conservative. Sometimes I teach a basic stats course to play it simple and do the smaller of 10 minus 1 and 16 minus 1, which would be 9, and use 9 degrees of freedom, and you'd get an even bigger p-value. Let me end this video by confirming both of these problems' answers with a table as well. So we'll go back to the variance problem. I did want to show you can use a table to approximate the p-value here. So we got this F statistic for the first problem with numerator had 5 degrees of freedom and the denominator had 9 degrees of freedom. We were testing at the 5% level. I've got this table that's got an F distribution for it. It's got CDF values on some previous pages of 0.9 and on this page of 0.95. That's the CDF value. That's the area to the left of the F statistic, meaning the area to the right is 0.05. So this is an appropriate table to use for a 5% level of significance. Again, the degrees of freedom for the numerator is 5, the denominator is 9. In this table, the numerator degrees of freedom is across the top, the 5 there, and the denominator along the side, the 9 there. The critical value for a 5% test is 3.482, and our value is bigger than that, and therefore we reject the null. Our p-value would be less than 5%. That's how you would use that table. And then for this one, I'd have to use a t-distribution table. For the first case, based on 24 degrees of freedom, 24 degrees of freedom, the t-stat for a, well, we didn't have an alpha here, but our observed t-stat was about 2.5. So that's between these two numbers, and that means the right-tailed p-value will be between 1 minus this number and 1 minus that number, between 0.005 and 0.005 and 0.01, which it is, okay? And for the other one, we had 17.7 degrees of freedom, approximately 18, although if you want to play it safe, you'd round down to 17. T is about 2.47, looking in the 17 and 18 degrees of freedom line. Both, that number is between, it doesn't matter which degrees of freedom you use, it's between these two. And the one-tailed p-value is between 1 minus this number and 1 minus that number, between 0.01 and 0.025, which it is. Okay, great. Thanks for watching.